Right, good afternoon everybody. Thank you for persevering and being with me during the graveyard shift phase. So nice to see you all. So I'll be giving a talk about filtration. I'm the Technical Director of Industrial Filtration Limited, a company based in the UK. So in our world, filtration is a process for separating things, typically a contaminant from a liquid or a gas. Sometimes you may even want to recover, whatever you're separating. So essentially what I want to talk about is how we can use filters within liquid cooling. So filters are not like the filters you see in your kitchen. They're not simple sieves. They're more sophisticated and can be manufactured from quite a wide array of different materials and can come in different formats. And the grade of filtration typically depends on the nature of the particle that you're trying to remove and also the size of the particle. So correct filter sizing is vital in ensuring economic performance of your system. So within filtration, there are three overarching mechanisms when it comes to removal. And for liquid cooling, we only need to focus on two. So those two are direct interception. So you can see in the yellow there. So direct interception works on the principle that the contaminant that you're removing is larger than the pores within the filtration medium that you're working with. The next mechanism is inertial impaction, and this separates contamination through a change in fluid flow direction and the principles of inertia. So this results essentially in the contaminant traveling in a straight line and being knocked out by the filtration media and thus removed. The third one, diffusional interception, that's more really for gases, and so we're not really concerned with that. So typically when we talk about filtration, we're talking units in microns. So 1 millimeter is equivalent to 1,000 microns. So typically the smallest thing that you can see with the naked eye is about 40 microns. So this is the diameter of the smallest, I don't know, the width of the smallest human hair you can have. So within process fluids, you have quite a wide range of different particulates that you're looking to take out. Some of them are relatively easy to remove. So hard particles like rust, sand, carbon. So they would typically remain trapped in the filter throughout the lifetime of the filter. Other particulates, such as fibers, gels, colloids, are typically a bit more difficult to remove and can unload, if the pressure increases. So I want to share a video that gives a good visual indicator of the type of particles that we're looking at size-wise. So we are discussing process filters, and process filters wouldn't be able to remove, let's say, viruses. You'd have to rely on membranes. The smallest particle that you can remove with a fine process filter would be 0.2, so would in essence be the smallest bacteria. So you can see a red blood cell there, 10 microns. So these are typically the range of sizes that we would be looking at within process filtration. So let's say anything from 150 down to 10 microns. Okay, so that was just to give you a good visual indication. I would like to give a glimpse of the filter media products that you would typically rely on to protect the liquid cooling systems and are taking over the exhibition floor space. They're all over the place. So the main product is the depth filter. Now, this is a very versatile piece of kit. It performs quite well in a wide range of different applications. It can remove quite a wide range of particles, whether it's a gel, colloid, hard particles, due to the nature of media. It has what we call a graded density and a tortuous pathway, so it makes it quite versatile. But the negative side is that it gives you quite a high, low, clean DP. And the other good thing actually is that you're able to remove quite a broad range of different particle sizes away from the labeled grade that you get given. Although if it's a bigger particle size, the efficiency rises up. If it's a particle size that is smaller, then the efficiency would go down with that filter. The next product that you would commonly use within the filter housings in liquid cooling systems would be pleated filters. Now, this is a brilliant piece of technology in the right setup, and context is really king when you're dealing with this filter. If you have a wide particle size distribution, forget about it. This isn't the product because you'll get clogged up very quickly. But if you find that your fluid is fairly clean and you know what your particle size distribution is, thus, let's say you've got a narrow particle size distribution, this is the perfect product because it will give you, in those conditions, great flow through, so you can flow through quite quickly through the filter, and also the clean DP will be quite low. So within the right conditions, perfect filter, and absolutely worth the higher price that you would normally pay on, in terms of difference between that and a depth filter. So word of warning, this isn't a great product if you find that you have, let's say, gels, colloids within your process fluid. They tend to kind of slip through due to the limited surface area. Not the surface area, due to the limited depth, of the product. So there are two categories of end fittings when it comes to process filters. So you've got what we call single open-ended end fittings and double open-ended end fittings, so commonly referred as SOE or DOE. So DOEs, double open-ended end fittings, are typically for non-critical applications. If the end user doesn't mind a few particles being downstream. So really they should be used to take out nuts and bolts. This end fitting, I think, shouldn't be used in liquid cooling due to the criticality of the application. The risk of bypass with this kind of end fitting is real. So what you have, in essence, is no seals on both ends. With the second type of filter or category of end fitting, which is a SOE, this is the perfect end fitting to use with liquid cooling because you have quite a high level of security. So this end fitting is quite expensive compared to DOE, and that's why a lot of filter vendors try to cut costs by not giving you a filter with an SOE. And the other thing is, filter vendors are notorious for locking you into their product by giving you a unique end cap that only they make. So what I would recommend is you stick to the standard end caps that are quite common amongst global filter manufacturers. So typically there's 4 types of end caps that are very common. So you've got code 7, code 2, code 8, code 3. Everyone manufactures it. So don't get locked in into a unique end cap. And the other thing is, if you're dealing with a filter that is 10 microns and below, using an SOE should be non-negotiable. You should not be using a DOE, and you should not be using a plastic housing either. So you should be using a highly engineered product, such as a stainless steel housing, that gives you a well-engineered fitting. So coming on now to absolute versus nominal rated issue. So this is something, again, I've not heard a lot, I've not heard it being discussed a lot within the data center industry. So absolute filters give you guaranteed filtration efficiency at the stated micron rating. So this ensures you get guaranteed repeatable performance. These are typically high-spec products with tight tolerances and engineered for optimum performance and longevity. So these are ideal for critical applications, the ones we're talking about, liquid cooling, direct-to-chip, etc. In contrast, nominal filters do the opposite. They don't offer you that repeatable guaranteed performance, and the efficiencies with nominal filters can be as low as 50%, okay? So these are typically low-spec products, cost-effective solutions, and suited for non-critical applications. So again, it's if the customer doesn't mind a few particles being downstream of the filter, so they would use a nominal product. This table highlights beta ratio efficiencies, which is commonly used in industries such as oil and gas, pharmaceutical industry, and food and bev. So having a beta ratio gives you a guarantee of repeatable performance. So what that shows you is that for a given micron grade, you would remove, let's say if you've got beta ratio of 5,000, so you would remove 99.98 of all the particulate above that given grade. It's good to see as well that ASHRAE is now a champion of beta ratio, so they're really pushing that into the industry, which wasn't happening before, so that's great news. The most common ratio used in the industries that I mentioned before, food and bev, oil and gas, is beta ratio 5,000. What this means is that for every 5,000 particles upstream of the filter, only one particle should make it downstream. And this efficiency should last for the whole lifetime of the filter. Okay. So just looking now at some OCP guidance. So in direct-to-chip cooling, filtration is really essential when it comes to protecting microchannels and cold plate geometries, which are highly sensitive, obviously, to contaminants. Key components like this are very vulnerable to particulate buildup, potentially blocking the flow of liquid, or flow of cooling liquid. So the filter size is really determined by the most sensitive part of the cooling loop, ensuring particles are kept out. So effective filtration here prevents system fouling, reduced performance, or leaks, or even system failure. So really it's all about maintaining the efficiency and reliability of the cooling system. So great presentation earlier by Keegan, Philip and Saha, presented a good update on guidance, and I used their submission also, the reference to requirements. So touching on treated water, biocontamination is a big danger as identified by Philip. So watch out for biofilm formation, and in fact biofilm can even form on the filters themselves. So you can mitigate against this by using zinc silver type microbial filters, but do watch out if you're using it in treated water. If the water has high resistivity, then you could have compatibility issues when using these microbial type filters. So again, there's different advice given when it comes to micron grades that should be used, but the rule of thumb within filtration, if you've got, let's say, a primary filter, that primary filter should be 5 to 10 times more open than the filter downstream of it. So with dielectric fluids, as Saha mentioned, pretty clean due to their nature. So what you should mostly be concerned about is the initial phases. So any debris from manufacturing, catching that commissioning debris. So making sure this doesn't affect, operations when you kick in to the operational phase of your system. With PG, very much as per water, except there is less risk of biocontamination. And based on my experience with the HVAC industry, even a 20 micron filter works well as long as it's an absolute filter. So maybe when you start up in the commissioning phase, you might have to use a coarser media grade to knock out the nuts and bolts that come from the commissioning debris, and then you can taper it down to the final grade that you want, whether it's a 5 micron or it's a 20 micron. So different filtration setups for CDUs. There's different permutations. That could favor full flow filtration or side stream filtration. So for let's say full flow filtration, that might be appropriate when you have a low flow scenario and you can harness the advantage of having that full flow filter where you can clean up quite rapidly and you have that precise filtration. So the most common filter material that you see out there is polypropylene. But be aware that polypropylene as a material does tend to start to buckle when you approach 65 degrees. So you need then a filter that has a more sturdy core. So typically what filter vendors would recommend would be a glass core to make the filter more integral. As I said, it's important to protect tight fin spaces, and the filtration that you have in place should be based on the gap sizes of the microchannels. So always ask as well the filter manufacturer what the efficiency of the filter is. Hands up, how many people use filters in the room? Okay, a few hands. How many people know the efficiency of their filters? Okay, just one person, and that's a big problem. Like guys, you really should know what the efficiency of your filters is, because let's say if you've got two products, they're both 25 micron filters. One could be 50% efficient, the other could be 99.98 efficient. The performance of those filters would vary drastically, and the 99.98 would knock out, as I said, the majority of particles, whereas the 50% efficient filter would let in 50% of all the particulate in your fluid stream. So it's not really doing its job. And for the filtration vendor, if they can offer you a low efficiency filter at the same price as a high efficiency, they'll do that because their profit margin is up there. So always ask what the filtration efficiency is of the filter that you're using. And this is especially important when you come to finer grades of filters. Some highlights on ASHRAE guidance, so around contamination control. So I've read some great documents from ASHRAE, really got me up to speed with data centers as well. I really kind of came into the industry about 2 years ago and transferring my knowledge from the HVAC industry. So ASHRAE has been really good in getting up to speed. A great cache of resources, so I advise you all go into the ASHRAE cache of documentation. And as I said, they are now becoming a champion of beta ratio. So that is great news. I'm rushing a bit now, I've only got a few minutes. So current challenges, there's a lack of definition with regards to efficiency. And this can lead to inconsistent results when it comes to performance. A lot of vendors as well, CDU vendors, are confused on what micron grade they should be using and why they are using certain micron grades. We should introduce standard lengths like you see in other industries. So food and bev, oil and gas, pharma, everyone knows you use 10 inch, 20 inch, 30 inch, 40 inch. But what you see in the data center industry is sometimes odd sizes, like 25 inch. And that means that vendor that's offering you a 25 inch filter has locked you in because nobody else can retrofit that easily. Likewise, the end caps as well. So introduce standard end caps and standard lengths. So I'm a strong champion of raising standards to achieve repeatable, guaranteed performance. And this also holds filter suppliers accountable to what they're doing. All right, so maybe going to beta ratio 5,000 may be a bit of a stretch and a bit of a bridge too far to go from having no standards. So maybe looking at beta ratio 1,000, meaning for every 1,000 particles upstream, only one particle makes it downstream. So I would also encourage the industry to adopt SEO, single open-ended end caps, due to how critical the application is. So having that single open-ended end cap will reduce the risk of bypass. And just a bit about industrial filtration, a bit about what we do. And as always, you know, engage with the work stream. And yeah, I'm a lot more engaged with the work stream now. So some great stuff coming out from the work stream, and hopefully we can build a bit more in terms of filtration into the work streams and help the wider ecosystem. So thank you.
We maybe have time for one question. Please come up to the mic.
Is there a consideration of pumping power, and when you do compare filters, that will be a good basis, apples comparison. So do you consider pumping power?
Yeah. So I mean, for filters to work, optimum efficiency, you need minimum of around 2 bar pumping power. So as long as you've got 2 bar coming through the system, you're fine. And with filters like depth filters, you need to make sure you have this because of how thick the media is. So typically as a filter supplier, we would look to give you a clean DP of about 50 millibar media-wise, and add in the housing pressure loss as well, about 100 millibar pressure-wise. So that's the clean DP, and you should be changing out at about 1.5 to 2 bar differential pressure.
All right, thank you.
Okay, thank you.